So the graph as you see it here was not the graph that appears in Kleiber's original 1947 paper on the relationship between body weight and calorie consumption or heat production. Right? The graph that you were given on the exam was the original graph from Kleiber's paper, and it looked like this. Everything's the same about it, except for what? What did I change to clarify the graph the second time around? The axes, right, because Kleiber's original graph, and this was probably something that was suggested to him by his data to do. He probably tried it a variety of different ways and wanted to figure out what was going on. But in his original graph, he's got a logarithmic scale on the horizontal axis, and he's got a logarithmic scale on the vertical axis as well. So this is what we would call a log-log graph. Log, log. Log in the x direction, log in the y direction. And the equation y equals 3/4 x plus 7/4 refers to the equation of this line, but this line sketched on log-log axes. So the hard part about interpreting what this line means in a specific sense is that because we have a logarithmic scale going in both the horizontal direction and in the vertical direction, we really have to be careful how we interpret a number like the slope. So what you might have done on the exam to interpret the slope of 3/4, might be to say, well, this really means a rise of 3 corresponds to a run of 4. In other words, a horizontal increase of 4 and a vertical increase of 3 on this graph are correlated one to another. But then you would have to ask yourself, well, what does a, for instance, horizontal run of 4 correspond to? What's happening to this animal's body weight when we proceed 4 steps to the right in the horizontal direction? Well, what happens in each step? In each step we multiply by 10. And so when we run by 4 steps in total, what are we getting? Yeah, we're getting multiplied by 10,000. So a run of 4 in the horizontal direction on this graph corresponds to a 10,000-fold increase in the body weight of the animal in question. And likewise in the vertical direction. In the vertical direction we have a rise of 3, which corresponds to an increase by what factor? Again, because each one of those units is a factor of 10, 3 of them is a factor of 10 to the 3rd power, so 1,000-fold increase in calories. So what the slope is telling you, if you interpret it on the original graph that Kleiber generated, is that if an animal weighs 10,000 times more than another animal, so for every 10,000-fold increase in the weight, the body weight of an animal, there is a 1,000-fold increase in the number of calories that they produce or need to consume to maintain their weight at a given weight. So that was how Kleiber and his colleagues would have interpreted his original graph. But the reason that it was kind of tricky to interpret the first time around is that we are so used to linear scales that in order to interpret what a slope of 3/4 means, it probably, and it actually I think is a little more conventional nowadays, so 60-some years after Kleiber's original paper, it makes more sense nowadays, just by convention, to instead present the graph that you saw today, where instead of graphing the body weights themselves and the calories themselves, you graph their base 10 logarithms. And in this case, again, it's the same line. So this line still has the equation y equals 3/4 x plus 7/4. Except here we've made it plain exactly how the y and the x, which are inhabiting the axes of this graph, relate to the body weight. So x is the log of the body weight, and the calorie consumption or production, which is the logarithm. Y is the logarithm of that. And so now, because our scales are linear, Now we can interpret the slope in the same way that we interpret slopes conventionally when we have a linear scale. And all we would have to say is that for every increase in the horizontal direction, so in the horizontal direction is body weight, so when x increases by 4, y increases by 3. Except now, we want to make a statement about weight and calories instead of x and y, which are our transform variables, so we'll just go back. Instead of x, we'll write the log of w, and instead of y, we'll write the log of p. And then all we have to do is figure out now what does it mean for the log to increase by 4 and for the log to increase by 3. And to interpret that, we just need to cancel those logs out by raising these statements as an exponent with a base of 10. In other words, when the log of p increases by 3, p increases by a factor of 10 to the third. There's our 1,000 from the original interpretation. And likewise, when the log of w increases by 4, w itself increases by a factor of 10 to the fourth. And you solve this transformed equation and you get some kind of a power function that the equation you actually end up with relating w and p specifically is something like p equals 10 to the power 7/4, which is 56 point something, times w raised to the power 3/4. Which, if we graphed that equation on linear axes, it would not be a straight line. It would be a curve. Looks kind of like a square root graph. It would be a concave down curve emanating from the origin.